Section 5.2, the definite integral. Now, before you view this section, you should have already read through section 5.1. I'm going to give a quick summary of that section, but I would recommend that you read through that section to have a clear understanding of all the notation and terminology that I'm about to use. So if you have not read yet section 5.1, you should stop now, go back and read that section, and then come back to this section. All right, so what section 5.1 talks about, it's leading us into the idea ultimately of the integral. That's where we're headed. And that's ultimately coming from the antiderivative that we talked about back at the end of chapter 4. Now, remember back when we talked about slope of a tangent line right at the very beginning, and how that led us to the idea of the limit. We took the slope of the secant lines and used the limit of the slope of the secant line to give us the slope of the tangent. Or we also talked about that in the context of velocity, where we used the velocity over smaller and smaller intervals, right, average velocity, to ultimately give us the instantaneous velocity, right, the velocity at a specific point in time. So, and then all of that eventually led us to the derivative, right, which was the rate of change in our position function, right, giving us the velocity function. So it gave some context, it gave some meaning as far as what the derivative actually represents. So the integral, or the antiderivative, also has some context. It also has some meaning. So it's talked about in section 5.1, laying the groundwork for what we're going to talk about in terms of the derivative. It's starting off with the idea of finding the area under a curve, right? To where if I have a function f of x and I want to calculate the area under this curve over the interval from a to b, so we have our function f of x, we have the interval from a to b, and I'm bounding this by the x-axis as well. And then I'm finding the area of the region enclosed within that boundary. And of course the issue is here, while I don't really have a formula for that, if it was a rectangle, there's a formula for finding the area of a rectangle, we know. There's a formula for triangles, there's a formula for circles, etc., etc. Or any type of polygon, with straight sides, I can always slice it up into pieces that are recognizable in terms of area calculations, and we can calculate the area of each little piece, cut it up into rectangles or triangles or what have you, and calculate the area of each of those pieces, and then we take the sum of the areas to give us the total area of the region. Well, that's the idea that we're going to employ here, because I don't have a straight formula, or at least not yet, for finding the area under this curve directly. What we do is we start by taking an approximation. And so we slice this region, or this interval, from a to b into what we're going to call subintervals or subregions. All right, so I just pick out however many regions I want to form, and then we divide that interval from a to b into equally spaced intervals or subintervals. And so the endpoints of those subintervals we label using the x-coordinate. Our a value, which is the left endpoint of our interval, we're labeling that as x sub 0. And then the right endpoint of our subinterval, the b value, is labeled as x sub n, where n is the number of subintervals that we have, right? So however many slices we care to make. So in this case, I have 6. So if we were to label that as a specific value, that would be x sub 6, because it's the right endpoint of our 6th subinterval. Okay, so each endpoint is labeled accordingly. So we have x sub 1, x sub 2, etc., 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 up through, say, x sub I, which generically represents, we call it the ith subinterval, which could be any subinterval. Plug in a value for I, and we're talking about that particular subinterval, all the way up to x sub n, right, which is the right endpoint of our last subinterval, which is our b value. The width of each of those subintervals, the distance between any of those two endpoints, is always going to be the same, because we're going to make it uniform. And we're going to call that distance delta x. That's the notation we've used before, back when we were mainly talking about differentials, when we talked about delta x and delta y, dx and dy, and what all those represented. So here, because I'm looking at the exact function, the graph, I'm going to call the distance between those x coordinates delta x. Okay? And it's going to be the same for each of those subintervals. But then the idea is, all right, let's use a region that we're familiar with, that we know a formula or have a formula for calculating the area of, and we're using rectangles in this case. Now, this is not the only process that can be used. If you're going into Calc 2, you'll also look at a couple of other formulas that are used, not just using rectangles, but you could use trapezoids, you could actually use parabolas. There's other forms or ways of doing this to get these approximations. But here we're just talking about the rectangles. That's the basic, and then we could deal with more interesting situations later. But the idea here is, look, let's take each of the endpoints of our subintervals and use those to calculate the height of a rectangle under the curve. All right, so like in this case, the case on the left, I'm using the right endpoint of that first subinterval to give me the height of that first rectangle. And then we form a rectangle there, where the width of that rectangle is delta x. We said they're all going to be the same. The height of the rectangle is determined by the function value at x of 1. So that would be f of x of 1. The second rectangle, I form the height by using x of 2. So f of x of 2 gives me the height. The width, again, is delta x. And then et cetera, et cetera. So I use this endpoint to form the rectangle, et cetera. For the ith subinterval, right? So however many we have here, this would be the height of that rectangle, f of x sub I, and then the width is delta x. So I form these rectangles, and then I take the area of each rectangle, right, which is the width times the height, and if I take the sum of the widths of the areas of those rectangles, then that would give me at least an approximation to the area under the curve. Now, obviously, in this case, it's a little over approximation because there's more area under those rectangles. Right? Each one has a little extra area than what's actually under the curve, but at least it gives me an approximation. What I did on the right side was, instead of using the right endpoint of the subinterval to form the rectangle, I used the left endpoint. So the height of the rectangle, the first rectangle, is at x sub 0, so that would be f of x sub 0. The width is delta x, and then I get this first rectangle, the area of. Second rectangle is formed with the height at x sub 1, so f of x sub 1 is the height of that second rectangle. F of x sub 2 would be the height of this next rectangle, etc., 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 right? So we're forming rectangles again, but we're choosing the height or calculating the height using the left endpoint of the subinterval instead of the right endpoint, okay? And then in this case, we would get an actual, kind of an under approximation, right? Because the area under the curve, there's a little extra area here and here that's not enclosed within the rectangles, etc. But again, it's an approximation. All right. So from the graphs that we have, I can make this observation visually and say, look, the area calculated by using the right endpoints, I just called that r sub n, is a little bit bigger than the area under the curve. The area calculated using the left endpoints, I called it L sub n, is a little bit less than the area under the curve, right? So at least visually I can make this observation that, look, the area has to lie somewhere between the two, all right? Now, theoretically, I could choose any point in each of those subintervals to calculate the height of the rectangle, right? So if instead of choosing the left endpoint or the right endpoint, maybe I choose something in between. Maybe I choose the midpoint, and I form the height of the rectangle there. And I choose the midpoint here, and I form the rectangle there, using that as the height. Okay, so it doesn't matter. I mean, you can pick any value in the subinterval to calculate the height of the rectangle. And we're going to call that number, let me not use that, the value or the x coordinate that we choose in the subinterval, we're going to call it x sub I star. Again, the I, remember, generically represents any of the subintervals, so whichever subinterval you pick from 1 to n. So I would go from 1 to n. And then we take a point in the subinterval, we'll call it a sample point, and so generically we're calling it x sub I star. It's just some point. So like if in this first subinterval, I would pick a value for x, call it x sub 1 star. It's the sample point in the first subinterval. Pick a point between x sub 1 and x sub 2 in that second subinterval, call it x sub 2 star, all right, to calculate the height of our rectangle. Bottom line is you're just picking a value between each of those subintervals or in each of those subintervals to calculate the height of the rectangle. You multiply that times the width, which is always delta x. Each rectangle has the same width, and that gives you the area of the rectangles. And then if you add the areas of the rectangles, you're going to get an approximation to the area under the curve. Now, the other observation would be this. the more rectangles you have, right? So in this case, I'm only using 6. What if I used 10 or 100 or 1,000 rectangles, right? Still within the same region, right? So the width here from A to B doesn't change, but I'm forming more and more rectangles in that interval. The more rectangles you have, I think it's reasonable to say I would get a better approximation, right? What if I drew 1,000,000 rectangles under there, right? You could picture that in your mind. Then all of these little extra, over and under approximations that we're getting become less and less and less, and so the rectangles give you a better and better approximation to the area under the curve the more rectangles there are. So theoretically then, we could let the number of rectangles approach infinity, right? The more rectangles I have, the better the approximation becomes. As the number of rectangles approaches infinity, then that should give me the actual area under the curve. It's the same idea as what we did with secant lines to give us the slope of the tan line, right? We took the limit of the slope of the secant line and we just kept moving our second point closer and closer and closer to the first point. We kept making the distance between the two smaller and smaller and smaller, which led us to that limit definition of the derivative, right, where the limit as h approaches 0, h was the difference between those 2 points on the secant line. And as that value approached 0, then the slope of the secant line would eventually give me the slope of the tan line. So this is the same idea. So if we let n approach infinity, the number of rectangles, the number of subintervals, and we look at the limit as n approaches infinity of the sum of the areas of those rectangles, we will get the area under the curve. So that's why, we keep coming back to this idea of the limit and why that idea is so important, because it's used in a lot of different cases to develop these little formulas that we use in calculus, and namely with the derivative and now with the antiderivative or the integral. Okay, so that's where this notation came from. And again, you need to make sure you're clear on the notation, the language, terminology here, because this is what we're going to use going forward. So first, I'm just ignoring this limit statement for a second. I'm going to start with this one. So if we take the area of each of those rectangles, right? So we said the area of the first rectangle would be its width, delta x, times its height, f of x of I, x of 1 star, whatever value I pick in the first subinterval. We add that to the area of the second rectangle, which again is delta x, the width, times the height, f of x of 2 star, etc., up to the last rectangle, whose area is delta x times f of x of n star, the sample point in that nth subinterval. And if you add all of those areas, you get an approximation to the area under the curve. But then we said if we continue to put more and more rectangles under there and let the number of rectangles approach infinity, then you're going to get exactly the area under the curve. Okay? Now, this notation is summarized. It's a collapsed notation. Instead of having to write out all of this each time I want to calculate the limit of the areas of those rectangles as n approaches infinity, because obviously I can't do an infinite number of rectangles, we use this notation, sigma notation, or what we call a Riemann sum. Now it's called sigma notation. This is the Greek letter sigma. It's a capital sigma. All right, kind of looks like a weird looking E thing, right? But it is the Greek letter sigma, and it represents. We use that in math to represent a sum. In other words, we're going to repeatedly add whatever comes after it, plugging in the different values for I. All right, so to say that the sum as I goes from 1 to n of f of x of I star delta x, we take whatever that counter is, the I in this case, and we'll replace it with values from 1 to n. Right? And that's what's happening down here with this one. So if we let I equal 1, we get f of x of 1 star times delta x, plus let I equal 2, f of x of 2 star delta x. Let I equal 3, you get f of x of 3 star delta x, etc., up to whatever our final value is, which is represented by n. And there's our f of x sub n star times delta x. Now again, if you fix the number of rectangles, right, if we say let n equal 6, for example, like we have in our graph on the left, then I would have the I go from 1 to 6. And I wouldn't need this limit statement. Okay. Now, if I let I equal 1 to 6, and again we calculate the area of the 6 rectangles, we take the sum of those areas, we're going to get an approximation to the area under the curve. But then we would like to give an exact area, so that's where we bring in again the idea of the limit as n approaches infinity, which would give us the exact area under the curve. So sigma notation, we also call it a Riemann sum. Riemann, another one of those famous mathematicians from back in the day, and he kind of get credit for the development of this notation, but that's what that notation represents. It's a sum notation representing or telling me that I'm going to add repeatedly whatever my expression is by plugging in the different values for I, starting at 1 up to whatever we specify. Okay. And of course, it doesn't always have to start at 1. It does in our case because we're talking about the first, second, third, fourth, fifth, etc. subintervals. But we'll see that notation pop up again elsewhere. Like I said, again, if you're going into, say, Calc 2, we do some more stuff with this Riemann notation, Riemann sums and sigma notation in different cases. So the counter doesn't always have to start at 1. Just depends on the context in which you're using it. All right, but that's the notation that we need to be familiar with, right? So, and especially what it means and what we're using it to calculate, all right? Now, again, what are we using it to determine? In this case, specifically, it's the area under the curve, right? Now, there's also another context for this. We want to put some meaning to it, right? So area under a curve, great. So I can calculate the area of a region. Whoop-de-doo. Well, just like with the derivative, right? We use that to calculate the slope of a tan line. We also used it in the context of calculating velocity. Remember, we could take a position function, s of t, find its derivative, which was the velocity function. It was the rate of change in position of an object. Okay, and so there was a little more meaningful context there. Well, the same thing is true here for the integral. If, let's say, this was a velocity curve, right? So let's say that that function is a velocity function, and I'm calculating the area under that velocity function. If you look at the area of that rectangle, right, the width times the height, if this is the velocity of an object over time, so as we move from left to right, what's their velocity at a certain point in time? If you look at the area of that rectangle, its width would be some amount of time, its height would be the velocity. Right? And if you take your velocity or your speed or your rate of travel over a certain amount of time and you multiply those together, right, width times height, what do you get? You get the distance traveled. All right, that's your basic little distance formula. Your distance equals rate times time, if you remember that one. But that's what you're looking at contextually here. If this curve is a velocity curve, right, then the height of that rectangle would be the velocity of your object. The width of the rectangle is the amount of time it traveled at that velocity. And if you multiply velocity times the amount of time spent at that velocity, you're going to get distance traveled. Like, for example, I traveled 60 miles per hour for 3 hours, right? Then I've traveled 180 miles, that idea. So it gives you position, or it gives you distance traveled. Now think about what that means in terms of our other functions, right? With the derivative, when we took the position function and the derivative gave me the velocity function. Well, and again, I think this would make sense too. If I take the velocity function, its antiderivative would be the position function. And it turns out that the area under the velocity curve is going to give you the distance traveled by your object. Now we have to be a little careful there in terms of what we mean by distance. We've kind of talked about that before. We've talked about distance versus displacement. We're going to talk about more about this as we go forward. But like displacement, you know, from point A to point B, kind of your straight line distance. What is my position at point B? What is my position at point A? And then I take the difference between those two, and I've got the displacement versus the distance traveled to get from point A to point B. So instead of, if I went that straight line distance, maybe I, took some route to get there. And so the distance traveled from point A to point B is not necessarily the displacement. Right? We've mentioned that concept before. We're going to talk more about that as we go forward. So just kind of be careful of what we mean by distance. But bottom line, the idea here is, look, the area under a curve can be calculated using this limit of sums of the rectangles as that number of rectangle approaches infinity. And this is ultimately what's going to lead us to the idea of an integral. And then contextually, it also is going to correspond to the distance traveled, or more specifically, the displacement of an object, if I'm looking at the area under the velocity curve. All right. So that's going to be part of our discussion as we move forward. So that's kind of a quick summary of what's in section 5.1. So again, go back and reference that as needed, but that leads us up to this notation, and so our discussion going forward. All right, so definition, the definite integral. All right, so this is going to make up the predominant portion of the remaining part of our course. Let's say that we have a function f that is continuous. There's our good old continuity again, right? That continues to pop up in a lot of definitions and theorems. That's why continuity was so important. So if f is a continuous function defined on some interval from a to b, if we divide that interval ab into n subintervals, right? So we pick a number of subintervals, call that n, of equal width delta x, and so we said we want the width of each of the subintervals to be the same. Once I specify how many subintervals I want, then if we take the distance from a to b and we divide by the number of subintervals, that would give us the width of each subinterval. Right? So delta x equals b minus a over n. And we let x of 0 be the left endpoint. So x of 0, remember that was our a value. And then each of the endpoints of our subintervals, x sub 1, x sub 2, etc., up to the last subinterval, which ends at b, which would be x sub n, or have a right endpoint of x sub n, depending upon what n was. So we let those be the endpoints of our subintervals. And then we let x sub I star, x sub 1 star, x sub 2 star, etc., up through x sub n star be any sample point in those subintervals. So we said generically x sub I would lie in the ith subinterval, whose right endpoint would be x sub I, whose left endpoint would be one less than that, right? So x sub I minus 1. Then the definite integral of f from a to b is given by the integral from a to b of f of x dx. That's how we read that. And that's going to be an equivalent notation for that limit of sum notation that we used earlier. So here's the f of x dx. Remember, delta x and dx are the same back in our discussion of differentials. Delta y and dy are not necessarily the same, but delta x and dx were the same. In this case, representing the width of our partitions, or subintervals. F of x sub I, well, that's just the height of the rectangle, and f of x sub I star, where that represents a sample point in each subinterval. So more generally, we can just call that f of x. And then we're replacing this limit of sum notation with that elongated s. Okay. So that's the reason for the elongated s, because it's representing the limit of sums. Right? And then we have our limits of integration, so we're actually told from a to b, right, from what point to what point. But that's the integral notation, and it is a notation that is used to represent the limit of sums, which is the sum of the area of the rectangles under the curve. Now, because f is continuous, right, here's our continuity again. Because f is continuous, the limit always exists. So it should always be a limit that can be calculated, and it gives the same value no matter how you choose the sample points. And that's because of this. right? Because we said if you fix the number of rectangles, like we did here, we had a fixed number of rectangles, then it would make a difference depending upon how you choose the sample point in each subinterval. And if you calculate the area of each of those rectangles, like we said, it's going to be different because we have a fixed number of rectangles. But if the number of rectangles approaches infinity, and think about what happens again to those rectangles, the width of each rectangle is getting smaller and smaller and smaller. The width is approaching 0. And so at some point, it doesn't matter what value you choose over each subinterval, the height of the rectangle is always going to be the same, because the rectangle's width is approaching 0. And so when you calculate an integral, you're always going to get the same value, right, in terms of this limit as n approaches infinity. So it doesn't matter what sample point you choose. All right, terminology, and again, here's the main part of this, so the terminology and the notation. This, again, is called an integral sign, right? Elongated s to represent that limit of sums. Integral from a to b of f of x dx. A and b are called limits of integration. A is called your lower limit. It's the left endpoint of your interval. B is your upper limit, the right endpoint of your interval. And f of x is called the integrand. Right? So we have our limits of integration, left endpoint, left limit, or lower limit, A, upper limit, B, and the integrand, f of x. Integration, right? Process of calculating an integral. So nothing fancy there. And you could, of course, have different variables, right? So like we did with our functions when we were differentiating and all of that, just make sure you're consistent with your variables. So if my function is a function of t, we could have the integral from a to b of f of t dt. If our variable is r, the integral from a to b of f of r dr. Integral from a to b of g of x dx. You know, so same idea with derivatives. If you were differentiating with respect to x, right, then you were finding f prime of x. If you were integrating with respect to your independent variable, then that's our dx, dr, dt, that notation. Now again, this is used to calculate the area under a curve, f of x, from a to b. All right, now, again, we have to be careful about what we mean by area here. So we need a little more specifics in terms of, well, exactly what do we mean by area? Well, with respect to one similar to what we just looked at, if my function f of x lies entirely above the x-axis, then we said this is the area that we're calculating, right? Then we can calculate that area. That's always going to give us a positive value because our function is entirely above the x-axis. And so when you talk about, say, those rectangles and the area of each rectangle, the height of each rectangle would be a positive value because it is f of x sub I star, which would always be positive because the function value is positive. But what if we have a situation like this, where part of the function is above the x-axis and part of the function is below the x-axis? When you calculate this area for the part that's below the x-axis, I call it a sub 2, that's going to give you a negative value. Because if you draw in those little rectangles there, the height of each rectangle is going to be a negative value. So the area there is going to be negative area. The area here is a positive value. The area here is also a positive value. So when we say area under the curve, what we actually mean is what we'll call the net area, not the total area. Okay? So it takes into account the fact that some of the area is positive, it's above the x-axis. Some of the area is negative, it's below the x-axis, and you're actually calculating the net area or the difference between those. So it's similar to what we mentioned earlier about total distance versus displacement, right? Displacement is one thing, simply your change in position from point A to point B, versus total distance traveled, which depends on the route that you took to get there. All right, so it's kind of along those lines. So I have to take into account the fact that some of my area could be positive above the x-axis, some area is negative below the x-axis. So when we calculate an integral, what we're calculating is the net area, not the total area. Now we're going to address this later Okay, and it's going to be kind of the same idea that we did when we were doing the total distance traveled. Remember, we did those applications. I would have to figure out where my area was positive, and I would have to figure out where my area was negative by finding those points of, those x-intercepts, right? So I need to know where the graph changed from being above to below the x-axis. And then we could maybe calculate the area of each of those regions and come up with a total area, okay? But we'll talk about that later, right? But it's along the same lines. Now, not all functions are integrable, right? So the next idea is, all right, so how do we actually then integrate these things? So, that's going to be our discussion going forward. If I set up an integral with an integrand f of x, how do I actually then calculate that integral, right? So, first of all, not all functions are integrable, right? So just because I write an integral doesn't mean I can actually integrate it. But we do have some, some specifics, some requirements, right, for a function, for an integral to be integrable. We do need our function to be continuous. If f is continuous, there's our good old continuity again on our interval from a to b. Or if f only has a finite number of jump discontinuities. Remember those jump discontinuities where we would have something like this, or our function would come in and then it would jump up to the next piece, and then maybe it would, jump up to another piece, that kind of thing. So, you remember, you can always kind of form little rectangles here, that kind of thing. So as long as you have a finite number of jump discontinuities, we can calculate the area, but we needed a fixed number. We can't have an infinite number of those because we would have to divide the function up at those points, right? But provided we have a limited number of those, then the function would be integrable on our interval from a to b. Right? Now, what's involved in actually integrating that thing or finding the value of the integral, well, that's going to be all the processes that we're going to have to talk about, right? And we're going to talk about some of these processes in this chapter. And if you're heading into Calc 2, that's the first part of Calc 2, is dealing with other processes for evaluating integrals, right? So some of that can get a little bit involved. It's a little bit tricky, compared to differentiation. Integration is typically a little bit more of a process, right? It's a little bit more involved there. So we'll talk about that as we go. But the idea is, look, I have to have the function continuous or a fixed number of jump discontinuities, and we can at least say that the function is integrable. All right, now how do we actually go about the process? Well, that's our discussion going forward. So there's something else I wanted to say there. Yeah, it'll come back to me. Theorem. If f is integrable on our interval from a to b, then the integral from a to b of f of x dx is equal to that limit as n approaches infinity. The sum as I goes from 1 to n of f of x of I delta x. All right, so this is simply a theorem stating what we already mentioned earlier, that if the function is integrable, then our integral from a to b of f of x dx is equal to that limit of sums, where delta x, as we defined earlier, is b minus a over n, right? The interval, the width of that interval from a to b, divided by the number of partitions. And x of I, our sample point, is a plus I times delta x. Now, if you think about that, x of I, if I start at a, remember a is our x sub 0, that's our left endpoint. And then if I add I times delta x, that's going to take me to the right endpoint of each of our subinterval. All right, so 1 times delta x brings me across the first subinterval. And then 2 times delta x will get me to the endpoint of the second subinterval. 3 times delta x to the endpoint of the third subinterval, et cetera, et cetera, et cetera. But remember, ultimately we said it doesn't matter what sample point you choose. But it gives us a way to calculate generically x of I. All right, so definition for, or specifically, what do I mean by delta x and x of I? All right, so we've got these two different notations now, right? We've got the integral notation and we've got that limit of sum notations. We can convert from one to the other. Right? And this may seem a little bit weird, at least part of it, but it's all based upon the definition, right? The first conversion is pretty straightforward, I think. If we're going to take the limit notation and express it in terms of the integral, this is actually pretty straightforward. It's going in the opposite direction that's a little bit more involved. So we're going to express the limit as n approaches infinity. The sum as I goes from 1 to n of cosine of x of I over x of I times delta x as a definite integral on the interval from pi to 2 pi. All right. So I'm writing this in the form of an integral. There's my interval, so that's my limits of integration. So I've got the integral, trying to get that, from pi to 2 pi. All right, so we're given the limits of integration. And then remember, this is an integral of f of x dx. Well, here's f of x just in terms of x of I, because of the sum notation where I have to throw in that counter, that subscript. So f of x is simply cosine of x over x. And then, as we said earlier, dx is the same as delta x. All right? So in converting from try this again, the limit of sums to the integral, it's simply a matter of writing our integral with the provided limits of integration. We have to be given those limits of integration. And then we're simply replacing f of x of I with f of x, and we're replacing delta x with dx. And that's all there is to that. So for the second one, the limit as n approaches infinity, the sum as I goes from 1 to n of 4 minus 3x of I star squared plus 6x of I star cubed delta x on the interval from 0 to 2. So again, there's our integral from 0 to 2 with our provided limits of integration of f of x, which again is just simply 4 minus 3x squared plus 6x cubed. All right, so I'm just replacing x of I star here with x. And then we replace delta x with dx. Don't read more into that. That's all there is to it. Going from the limit of sums to the integral. Now, going from the integral to the limit of sums, that's a little bit more involved, because in the limit of sums notation, you have to define x of I, and you have to define delta x, right? So the reason we don't have to do that, or it's a little bit more straightforward going from the limit to the integral, is because we're given the limits of integration. Here we're not given notice in the limit of sums, there's no specification on the actual interval, right? Whereas before here we were told what interval we were integrating over, right? 0 to 2 or pi to 2 pi or what have you. So here I've got the limit as n approaches infinity. Sum as I goes from 1 to n, f of x of I star delta x. So we have to define x of I, we have to define delta x. So for this integral, I've got the integral from 1 to 10 of x minus 4 natural logs of x dx. So we want to express that as a limit of sums. So we have to find delta x. We have a definition for delta x though, right? Delta x is b minus a over n. We have our limits of integration, so there's our a value, and that's our b value. So from b minus a, 10 minus 1 over n, I get delta x equal to 9 over n. And then we previously defined x of I as a plus I times delta x. So a, which is 1, our left endpoint, I times delta x, which we just defined delta x, is 9 over n. Now again, this I is used as a counter. That's not our imaginary number or anything like that. So x of I, which is our sample point, is a plus I times delta x, or in this case, 1 plus 9 over n I. So then I could take the integral from 1 to 10 of f of x dx, and I'm just calling this r sub n because remember we said we're actually using the right endpoint, so that's not such a big deal. But I am representing it then as the limit of sums. I've got the limit as n approaches infinity, sum as I goes from 1 to n of f of x sub I. So we take our x sub I, plug that into f of x. So I've got 1 plus 9 over ni minus 4 times the natural log of 1 plus 9 over ni. That's our f of x of I. Times delta x, which we found to be 9 over n. Okay. I'll leave that up there for a second. Yeah, so that's a little bit more funky, right, in terms of that shift or conversion from the limit or from the integral to the limit of sums. Right? But you have to find delta x, find x of I, and plug those in. Okay.